Hey guys, welcome. Yeah, so problem 2 here, and this is easily my favorite problem because it looks hard and intimidating, but it's actually a fun and simple problem. All we need is an idea from Calc 2. So, to start, I think it'd be really helpful if you wrote the square root, the cube root, the fourth root, and so on using parentheses. So to start, what I'm saying is write integral, and then it'll be like a bunch of stuff to the 1/2 power dx, right? And what is this bunch of stuff? Well, everything is affected by the square root. So everything is affected by this 1/2 power. But this x is only affected by this 1/2 power, right? So we have this x here that's only affected by the square root. But we are multiplying it to other stuff, right? This x. We're multiplying it to an x and a bunch of other stuff that's affected not just by the 1/2, but also by a 1/3 power, right? Okay, cool. So now this x is only affected by that 1/2 power, but this second x is affected by the 1/3 and the 1/2 power, right? And then this x is in turn multiplied to a bunch of stuff that is to a 4th power, and we have an x here. So this x now, this third x, is affected by the 4th power, the 3rd power, and the 1/2 power. And you get the pattern. And then next we'll have an x here, right? And a bunch of stuff multiplying it, right? Where the bunch of stuff multiplying this x is put to the 1/5 power, but this x itself is only affected by the 1/4, 1/3, and 1/2 powers, right? Okay, sorry. That's right? This x is only affected by the 1/4, 1/3, and 1/2 powers. Whereas the next x that'll be in here will be affected by the 1/5, 1/4, 1/3, and 1/2 powers. Okay, cool. Enough said. Now, let's make use of all this stuff that we said about this x is affected only by that and yada yada. So if we make sense of that, what we're saying really is that the given integral is the same as x to the 1/2, which is this x, which is only affected by the 1/2 power, but it's being multiplied. Multiplied by what? Multiplied by the next x, which, well, to start, the next x. It's multiplied by everything that follows, but first by this x. And this x is put to the 1/3 and 1/2 power. So the second x is going to have 1/2 times 1/3 as its exponent. And then in turn, this is multiplied by x to the, and now this is the x I just wrote. And this x is to the 1/4, to the 1/3, and then to the 1/2. So it's to the power 1/2 times 1/3 times 1/4, right? Okay, now we don't even need to think to know what the next x will have as its exponent. It's clear that it'll be 1/2 times 1/3 times 1/4 times 1/5, right? And we continue in this fashion. So I'll just say ... and then dx, yeah? Okay, cool. And look at what we've got. We've got that this is equal to the integral of x to the what? Well, notice I can write this as 1/2 factorial. This is 1/3 factorial, 1/4 factorial, 1/5 factorial, and I prefer that. So 1/2 factorial times x to the, that times sign was perhaps not necessary, but yeah, 1/3 factorial, and then x to the 1/4 factorial. I don't like that one. Like, it almost didn't want to be written. Okay, 4 factorial, and then times x to the 1/5 factorial, and ... dx. Okay, cool. I know how to make sense of this. That d. Okay, that's better. Okay, and now look here. Since the bases are the same, we can add the exponents. So the exponents will have the sum x to the 1/2 factorial plus 1/3 factorial plus 1/4 factorial plus 1/5 factorial plus ... Yeah? Okay, cool. And then, of course, dx. Got it. Now, look here. All we have left to do is figure out how to add 1 over 2 factorial, 1 over 3 factorial, and all that good stuff. So if we can figure out how to add the exponents, then we can make a lot of progress. So where did we first learn how to add things like 1 over 2 factorial, 1 over 3 factorial, and so on? How did we learn to add stuff like this? Well, we recall in Maclaurin series lessons that e to the x is equal to the infinite sum, n equals 0 to infinity of x to the n divided by n factorial. We know that this is e to the x, right? And look at what happens if we write term by term versions of it. Term by term, when n equals 0, we'll get 1 plus, when n is equal to 1, we'll get x over 1 factorial, which we can write as just x, so let's just write x. So we have 1 plus x, and then plus x squared over 2 factorial, and now we start smiling. Daylight, x cubed over 3 factorial, plus x to the 4th over 4 factorial, plus ... Yeah? Okay, cool. Now, look here. If that's e to the x, what would be e to the first, or simply e? Well, that would just be this stuff where x is 1, right? Because e to the first would mean we replace this x with 1, which means we replace that x with 1, which means we replace all of these x's with 1. But 1 to any power is just 1. So the sum, e to the first, which is e, becomes 1 plus 1, which is 2, and then plus 1 over 2 factorial. Yeah, plus 1 over 3 factorial, plus 1 over 4 factorial, and yada yada, plus 1 over 5 factorial, and so on and so forth. So, what are we saying? What we're saying is that e minus 2 will be exactly the exponent we've been after, because if we subtract 2 from both sides of this last equation, then what we'll have is e minus 2 will equal all this junk. Yeah, that's what we've been after. So our integral now is just the integral of x to the e minus 2 power, and then dx. But e minus 2 is just a number, right? So we could just use the power rule backwards, the power rule for derivatives backwards, and find that the antiderivative of this is x to the e minus 2 plus 1, so x to the e minus 1 divided by e minus 1, and then plus c. Yeah? Okay, cool. All right, I hope you enjoyed this, and keep watching. Take care.